Hello everyone, this is a repair of a Keithley 610 electrometer. This is an instrument that can measure very small currents and very large resistances. That's basically extremely high input impedance. So it's got some special uses for measuring insulations and other kinds of materials, as well as to measure small leakage currents. And actually it's a useful instrument if you're looking at vacuum tubes or other types of equipment that you want to repair. Anyway, this one is not working. It does not draw any power from the mains, nothing lights up. So I've already done some work on it, that is to remove certain things and clean up the insides. As you can see, there's some work already done. Show you that the main problem was the transformer was dead. It had leaked some shellac or whatever material they fill it with inside, and it used to sit over here, and you can see some of the drips of the brown liquid that came off and fell on top of the tubes, and also on the chassis down here. Anyway, it's been cleaned up, and the transformer I measured was open. Some of the windings were open, and so I had to reconstruct it, or actually had one rebuilt. So the transformer, the old one is this one over here. It's got something like 15 different inputs or outputs, several shielding windings, and some filament voltages for the tubes, a couple of them, and there's some couple of high voltage windings. Basically this is not available as a part that you can buy anywhere. So I had this made custom, and have the new transformer. That's this guy over here. I tested this transformer, and it seems to meet the voltage requirements that the original had, and also the current drive on each of the windings. I had to look up the schematics to check all that, and basically I came up with the specs for this transformer, and I sent it off to be made. I will describe later the process for that, as well as give you some insight as to what you want to do and how you want to specify the design for a transformer, and also the manufacturer if you want to have one similar one built for a different application. So next step is to put this transformer in here and route the wires through the hole down there into the other side where it connects to the rectifier diodes, which are down there. Actually there used to be selenium rectifiers, and those unfortunately some of them were not working. So this is what a selenium rectifier looks like. It's a stack of, in this case actually there were 15 in one of the stacks here, and it's just mounted vertically here. And I removed all of those. There were 4 of these. There was a 280 volt winding and a 160 volt winding, if I recall. And there's a significant voltage drop on these rectifiers because each of these segments here will drop about a volt or so. So you'll get about 10 volt drop. And these can't carry much current either. So these are the new rectifier diodes, and these are simple silicon diodes now, and they can easily handle 1000 volts and 1 amp. So off this goes, and I have the new diodes, and I had to size of course the voltage a little bit lower because of the voltage drop is much less here. The forward voltage is around close to maybe 0.7, 0.8 volts. So now I need to hook up these DC outputs that go into the rest of the chassis and to the different circuits here. Once I have that done, I will do a power up to check if there are any open shorts or any problems in the voltages after they are connected, and we'll go from there. Okay. So the transformer is now placed in there. And now I need to route all these wires through that small hole at the bottom, bring it to the other side, and then start soldering once I make sure I get all the wires correct. So that's my next step. I'll see you after that. Okay, so all the wires are through. You can see I'm highlighting that area. All the wires have gone through, and now I'm going to turn it over and check what's on the other side. So the wires are all bunched nicely together. First, the filament wires are here, these set of 4, and the high voltage are these bundle over here. I'm sorry, this is the shielding wires. The high voltage ones are these 4 over here, and the mains incoming are this, okay, the 2 blues and the blacks, so somewhere in there. Once I get that in, I'll start the next step of it is to check the voltages once reconnected. I have connected all the wires from the transformer to the input side of the DC supplies without having connected to the loads, but just want to check if the voltages are okay and make sure that no shorts on the secondary side. You can see the yellow wires there going to one of the filaments. The 2 green wires go to another set of filaments, and then there are 3 wires, the orange, gray, and violet, that go to the shields. And there's some other wires, red, browns, which are the high voltage 270 volt and 180 volt secondary side. So I'm going to power up the unit slowly through my variac, which is over here. Right now it's off. I'm going to turn it on. Right now it's got a single current limit, that is a 40 watt lamp in series, so voltage is at 0. The input is now turned on, so the power switch is on. And so let's crank up the voltage slowly. So as you can see, there's a slight glow on one of the lamps. That means it's taking current but is not shorting. If I turn on the second lamp, it should allow the voltage to go up a little bit higher. And weakly lit, there's a 10 watts of power being used right now. Turn on the third lamp. You're almost at 120 volts. So nothing's burning here, no shorts. I should probably try and measure voltages on the DC side. So let me put this away and try and mount this camera before I can do some probing here. Okay, I've connected all the DC side loads so that the capacitors can charge and create the proper DC voltages. I'm going to now power up again slowly. This time I should expect to see a lot more power being drawn, and you can also observe the tubes light up this time, and I'll turn off the lights for that. So let's power up the variac again. On, let's crank up the voltage. Meter on. so not quite 120, so I'm going to go for full power, and this time all the limiting current devices will be off, so now hopefully there's no shorts to blow this thing up, but here goes. Now it can take full current as it needs to. So that's 120, and everything looks okay here. I do have a probe on one of the DC large high voltage capacitors here, as you can see, and also we'll check the tubes in a minute. As you can see, the meter is reading 277 volts on one of the DC supplies. And now you can see the tubes glowing very nicely. And let's look at what happens if I just turn the meter to one of the positions here. It does respond. I don't know what it's doing right now, so I'm just gonna since I haven't used this instrument before, I'm not too familiar with it, I'm just gonna check other things, the DC stuff, before I play with it. So the meter off, I guess this is the meter off position. There's a positive and there's a negative and there's a zeroing function. I don't know if these make any difference. So the voltage scale does respond here. I don't know what it's measuring at this point, but sorry for the focus issues here. I don't know what's going on. But I think the power is about 40 watts, which probably is okay for this instrument. I'll have to check the specs on this later. But overall, it seems to be doing something, but I don't know if it's working. There's a lot of things to look at. I'll have to check the other DC voltages on this. There are 4 DC voltages to check, and also I've got to adjust them as well to the right values. So that's day 1 of this project. So far so good. This is the overall schematic of the Keithley 610A electrometer. Hopefully you can see this if you zoom in, or if you zoom into this video and on a full screen. Basically, to give you an overview of the whole thing, it's actually contained in one page. It's fairly compact, but it's hard to understand. This quality of the schematic is not very good, at least in this version. I can't tell in some cases where the lines cross or whether they actually connect. As you can see, there are some artifacts on the schematic which are difficult to see, and in certain areas the connections are not very clear. In any case, my focus is really on the transformer over here. So let's zoom in and take a look at that. Here we are looking at the transformer close up. Hopefully this is clear. As I mentioned earlier, this transformer basically has 2 secondary windings, S2 and S1, and 2 primary windings configured either as a 120 volt or 240 volt input. There are 2 filament windings, one of which is used as a floating supply, and one is connected more like a ground terminated on the cathode side. So they are separated because they are electrically isolated. Now, as I mentioned earlier, I did not have the specs for this transformer, so I had to derive them using the schematic, try to find the voltages, and then go back and then figure out how much current they were supplying. So there are some clues over here. For example, you know the voltages on some of these plate of these tubes, like this one, over here and over here. These are mentioned on the service manual. And based on the voltages that there were some test point voltages that were indicated. So based on that and knowing that there's a resistor, for example, between these two voltages, you can calculate the current through it. And if you add up all the currents that flow back or into the transformer, you can figure out what the current rating should be. There's also selenium rectifiers here. Of course, these drop a lot of voltage in terms of a regular, compared to a regular silicon diode. So if this is 15 volts, for example, 3 stacked with 5 in each stack, so you can assume this is going to be a 15 volt drop here and a 10 volt drop in this one. Now the currents, most of the currents that are flowing are in these regulator tubes over here. These are the cold cathode tubes 0A2, 0B2 and 0B2 over here. So if you know that most of the currents is really here, you can approximate the total current to be a sum of these currents, and the amount of current flowing in these tubes is quite small, in the order of several hundred microamps. So the total current I figured was about 20 milliamps in this leg, 24 milliamps in this leg, about 22 milliamps in this leg, and about 8 milliamps in this leg. So I specified the transformer to be about 70 milliamps to be conservative. Now also you can work out the voltages, because you know the voltage here is minus 150 volts, and if you work backwards you'll see that over here you would need about 370 volts and about 250 volts in this case. To arrive at the transformer specs on the secondary, we know that we need a DC voltage of about 250 volts. This is not a full wave rectifier, this is a single wave rectifier, so we'll assume there's going to be a drop around in the negative portion of the sine wave. It's not going to be recharging it. So the ripple is going to be a little bit higher than in a full wave rectifier, since you can see there's only a single diode and there's no reverse path for the positive supply, and similarly for the negative supply. So I'm showing here a positive rectifier here, in this case for the upper winding. So you see it's plus 250 volt requirement, and then the peak to peak voltage on the secondary side of this transformer would be 500 volts. So the RMS voltage will work out to be 177 volts. So I conservatively picked a value of 180 volts, and if you have a good filter capacitor, you probably won't see much of a drop with this 20 milliamps or so of current. So you can actually simulate this and then check if you like, but in this case 180 volts was a good number to shoot for. This is a conceptual schematic of the electrometer. I got this from the service manual. Amplifier A is actually the input stage, which consists of the electrometer, which is consists of 2 tubes which have very, very high input impedance, and they claim something like 10 to the power 14 ohms, which is like 100 tera ohms. There's also some internal means to make sure you get a proper zero, and following that stage is a differential amplifier, which then feeds another amplifier which converts that to a single-sided input, which drives this cathode follower. The cathode follower itself drives some other stages which are shown in the schematic, whose output is the amplifier output or the electrometer output. The critical voltages here are the plus 225 volts here, which if it's set correctly, based on the other resistances which are very, very accurate, you should get the correct gain. The input itself is not, there's no input divider, so the input impedance is always constant. What they do is they do a control on the feedback side on the cathode follower to get the right amplitude for different ranges. the separate grounds. One is the amplifier ground over here, which is floating ground, and the output ground is actually over here, which is coming off the center tap of this supply. So to give you an idea of where those tubes are, here's the electrometer input tubes, which drives the zeroing circuitry, the fully differential amplifier here, that gets single-ended converted here into this pentode, which then drives the cathode follower over here. The meter itself is over here, and it has a positive and a negative setting. That means you can measure either positive or negative voltages. It's also got a zero center display, which means the meter will sit at the midpoint in case you want to look at both positive and negative at the same time. There are some other controls, such as for calibration. The 225 volt is basically controlled by adjusting this potentiometer. The 100 volt internal voltage is set using this potentiometer. The zero is set by this one, which is in the front of the instrument. There's also a coarse zero at the back of the instrument. The four major adjustments that need to be done to calibrate this instrument properly are the 100 volt adjustment over here. There's a 225 volt adjustment over here. There's a zero center, which is for the meter zero, and a meter cal, which I think is a scaling factor for the meter. This I have not adjusted. I adjusted these two slightly to bring it into spec, and the meter center was also very close to what it should be, so I didn't touch that. This is the final shot of the inside of the chassis, with the transformer properly connected, all the wires shortened, and everything cleaned up. The output DC also are now shrink wrap connection made to them, so they don't fall off easily or break off. I've now hooked up the instrument to the main power supply, external 120 volts directly to the supply without the variac. I'm going to power on and see what happens. So now it's in the off position, which means the meter is off, but it's now powered on. And at this point, the tube should be working. So as you can see, the tubes have now lit up and nothing is blown up, which is a good sign. Because the meter is not reading anything since nothing is connected. There's no input, so it's still zero, which is a good sign. This is the multiplier, which basically allows you to on the volt scale will basically mean this is a 1 volt full scale, 0.3 volt. I can see it now deflecting a bit, and this is 0.01, and this is a zero control, and it actually seems to be working. And this is all the way up to 100 volts, returning to 1 volt, meter negative, center zero. So everything seems to be working as far as I can see. Now to connect maybe do a voltage measurement. Let me get some cables to connect to the front, and let's check that. Okay, just want to let you know that I have actually adjusted the 100 volt and the 225 volt supplies to the right value, and I will show you those controls in a little bit. So this should be now a very accurate instrument if the resistors are fine. There's no other tuning requirements to be done. So I'm going to turn on an external supply which is connected to this cable which goes to this PL259 plug, and let's see on the 1 volt scale. If I put in a 1 volt, I should get a full scale reading there. So right now it's in the 0 check position, so if I flip this up, it'll be in the operate position. Alright, nothing happened. Meter's off. Okay, that's good to turn it on. So it's on. Output's gone negative, and I think it should settle out, I think, a bit. There you go. So it's very close to 0. Now operate, and it looks very close to be on very close to target value of 1 volt. I should probably let it warm up a little bit, but I'm pretty satisfied with the accuracy of this instrument. Let's switch to a different voltage. Now I'm operating at 10 volts. Perfect, 10 volts. And now 3 volts. That's 3 volts. Now let's switch to 1.5 and see what happens. Right on mid scale. That's perfect. If you switch this to the 0 center, it should go to the plus 3 volt side, and that's plus 3. Okay, now I'm going to be doing a resistance measurement. The highest value resistor I have with me right now is a 1.5 mega ohm. So that's connected over here. We can see what that looks like. So I set it to the 10 to the 6 scale, multiplier of 3, so a 1.5 mega ohm should be right in the middle over there. And that's perfect, 1.5 mega ohms. So if I go on the 10 scale, it should drop to 1.5 on the upper scale, which looks pretty good. So overall, I think this instrument is working fine. No further calibration, I think, is required. I just need to get the bulbs replaced for the meter, so right now I don't have the right bulbs. The original ones were burnt out. Right now I put in a 12 volt bulb, which is way too dim, and I need to get the 6.3 volt bulbs. Hopefully that will brighten the display. So this concludes the Electrometer demo repair. I need to check the current ranges. For that I'll probably have to do a separate setup, have a different setup, make sure it's a little bit more challenging, I think, to do the current measurement. I need a current output, constant current output. Anyway, I'll do that later, but for the most part the voltage and the resistance measurements look good. I can try some really high resistance insulation resistances, and I think that should basically confirm that this meter is working across all ranges. Thank you.